Hi everybody, so this is going to be the first video about your acids and bases unit project, and to start off we have to look at what an acid and base is. So when we talk about acids and bases, we have to think about that, back in the day, or even before acids and bases were defined, there weren't any categories of defining these specific types of chemicals. So what that means is that it's not like our world started with acids and bases, and it's like, oh, this is an acid and this is a base. It's basically based on chemists looking at the properties of acids and bases and looking at, hey, this one, this chemical shares this property, this one also shares this property. Let's categorize them into this. All right. So when we talk about acids and bases, the properties of what defines an acid are the ones on the left side. Let me just kind of get my pen here. Excuse me. So we have acids being an electrolyte. That means that it can carry and conduct electricity. When you put acids, metals into acids, it will react with the metal. Generally, acids will taste sour. So if you think about, your orange juice or lemon, that is a very sour taste. And it will change colors when it goes into a litmus paper. So whenever you have a litmus paper that turns red, it is a property of an acid. Whereas if we were to talk about the properties of bases, bases also are electrolytes, but they're also slippery to touch. So when you think about, if you ever touch like Drano, which you shouldn't, but it is very slippery to touch. But like soap is a slippery to touch. That is a property of a base. And generally, bases contain a hydroxide ion, and we're going to see like why generally and not for all cases. Whereas acid will contain a proton or a hydrogen ion. And for bases, it will turn litmus paper blue. So one really easy way for me to remember, hey, does base or acid turn litmus paper blue? I just look at the first letter of base, and this will look at the first letter of the color, which is blue. So if you look at the first letters of each of them, base will turn litmus paper blue. If you're using the blue litmus paper to start off, then base will stay blue, right? So anytime you get the blue litmus paper, it means base. So when we talk about the acids of base definition, it sort of started off with two theories. The first theory is from a guy named Arrhenius, Arrhenius. And here's the guy, here's the fella. He won a Nobel Prize in 1903 for his look at the sort of the dissociation of your chemical compounds. And if you think about the dissociation and the conductivity, that is a really unique and specific property for acids. So when we look at Arrhenius' theory, this is the one that you have been used to. And if you look at hydrochloric acid, for example, right? Hydrochloric acid, it has HCl. So according to Arrhenius' theory, basically any acid is the one that dissociates into an H plus, or any proton. So we're going to call this H plus a proton because remember, proton is the one that has just a positive charge and no electrons, just like a hydrogen atom, because in order for this to gain that positive charge, it has to lose the electron, right? If you lose an electron, it'll become positive. And in this case, for hydrogen, since it only has one proton and one electron, if you lose the electron, it is exactly just like a proton. So for the acids, again, it will dissociate into your H plus. And if you look at the next one, this is sulfuric acid. Excuse me. It will dissociate not into just one, but two positive protons or hydrogen ions. And hydrochloric acid actually is a stronger acid than HCl because it dissociates into two hydrogen ions. And for the next one, this is your acetic acid. This is your vinegar. Your acetic acid, if you look at this, it actually dissociates into, again, this H plus, and then this CH3CO negative. So you can see that for all acids, really, you have this common proton that gets dissociated, and that's what Arrhenius' theory describes. And if you were to look at this particulate model, you can see that this is your HCl, and when it goes in this solution, these are H ions right here, will dissociate from your chlorine ions. Okay, that's what it will look like in solution. So what would it look like in a base if we were to scroll down here? In a base is exactly the same, except that for base, Arrhenius describes that hydroxide ion would get dissociated. So you notice that they all have a hydroxide ion, and that calcium hydroxide actually has two hydroxides that get dissociated out. That will make it a stronger base, because for every one molecule of this or one mole of this, you actually will have two moles or molecules of your hydroxide, so which makes it a little bit stronger than the other ones. But the problem here is that the problem we'll run into Arrhenius' theory is that all of these ones do dissociate into your positive hydrogen ion or hydroxide ion. But what about NH3? This is your ammonia. Ammonia is indeed a base. It exhibits all the properties of a base, but it doesn't have a hydroxide. So the problem with Arrhenius' theory is that ammonia is a base, but it does not contain hydroxide ion. So do all bases have to have a hydroxide ion? This is where his theory gets evolved into Bronsted and Lowry's theory. So Bronsted and Lowry, both of these were working on this independently, but they both describe an acid and base a little bit different than Arrhenius's. So instead of defining acids and bases with the dissociation of H plus or OH negative, now what they're saying is that acids and bases are actually based on the movement of this H plus. So in other words, they said that instead of looking at dissociating this H plus, an acid is defined as this proton donor. So any compound that donates a H plus is an acid, and a base is where it takes in this H plus. So anything that accepts a H plus is a base. This will eliminate the use of hydroxide ions, and we'll still see the hydroxide ion come back because it is dissociated from the water. But let's just look at this. Here's an example of what that means. So your hydrochloric acid is right here. Usually we see, according to Arrhenius' definition, that this gets dissociated into H plus and then Cl minus, and this is all AQ. But then, according to Bronsted and Lowry's definition, HCl is a proton donor. So that means that this H plus actually will get donated into the water, because again, remember, this is aqueous, it's in water. So then what happens is that this water molecule will get this additional H plus, which will get you this H3O, and this H3O is actually quite important. This is your hydronium ion. So this is the hydronium ion. Take note of this name because you're going to see this again. This is your H3O plus. And since your HCl has sort of lost or donated its H plus, now it's this Cl minus. So why is this a acidic solution? Because we don't see this positive H. So then this is actually your hydronium. This makes your solution acidic. All right. This is the reason why it makes your solution acidic. So hydrochloric acid reacts with water by donating protons. If we were to look at a base, how is ammonia a base now? Well, remember, in Arrhenius' theory, it's about your hydroxide, whereas Bronsted and Lowry is talking about the movement of H+. And a base is where it accepts a proton ion. So when ammonia gas is sort of dissolved into water, what happens is that the water actually becomes sort of the acid. It donates a positive hydrogen ion. When your ammonia accepts this positive ion, it gets this extra hydrogen ion, which makes it positive, right? That's where the positive charge comes from. So this is your ammonium, which you have seen before, ammonium ion. Well, if water lost or donated a H+, then now it becomes a negative charge, which is your hydroxide. So you can see from Bronsted and Lowry's definition, this makes sense. This hydroxide actually is the reason why your solution becomes basic. So ammonia accepts a proton from water, making ammonia a base, and water the acid. And we're going to classify these names. It's really important for you to recognize which one is your proton donor, which one is your proton acceptor, because now in Bronsted and Lowry's theory, that's what defines an acid or base. All right, so this is your introductory video. Watch the next one about how we name the conjugate base and conjugate acids, because that's where you can look at the products of product side and see how it becomes the base and how it becomes the acid. So thanks for watching.